This is our second formal lab, the Plato Resistor Lab, and it's by Marshall, Dalton, and Sydney. So first we have the circuit. It's drawn quickly over there on the left. So you have the batteries represented by those two lines with the larger line showing which way we're traveling along the circuit. And then it goes into a resistor, which is our Plato resistor, and then it branches into two um, paths. One is the LED, which is shown by that triangle and line, and the other one is denoted as the fan. So here's a picture of our resistor. On the left, you can see our Plato resistor modeled after Mickey Mouse. And then on the right, you can see our circuit itself. As you see, the LED and fan are both activated at the same time. Now we're getting into the numbers, the resistance of our resistor. So we measured the voltage and current through the resistor, LED, and fan, and those are the numbers that we found. And then using these values, we were able to find resistance. So for the resistor, we found it to be 36.4 ohms. The LED had a resistance of 276.92 ohms, which is a fairly large number compared to the fan, which had a resistance of 30.77 ohms. We found the voltage and current of each object with the multimeter and calculated resistance from there. We had to do some rounding, but eventually all the values fit together and made sense using the equation voltage equals current times resistance. The resistance of the LED was much higher than the rest, which was not expected. Um, by using three 1.5 volt batteries, our total voltage came to 4.5 volts. Even with all three objects in our circuit, the fan was able to spin and the light was able to light up. We attribute this to using black Play-Doh that has low resistance, and it was a small resistor that we made. This allowed enough voltage for both the fan and the light as they were in parallel, and therefore splitting the current. Similarly, the fan needed at least 300 milliamps to spin, and our setup allowed for more than enough. So here are some sources of error. So first, the Play-Doh. The dryness level of the Play-Doh led to a change in resistance, as we saw in the pre-lab. And that's hard to control for as the Play-Doh dried up pretty quick. And to get the whole circuit working at once with our resistor, it takes a little bit of time. And by then, the Play-Doh had dried to an extent. And also the size and connection to the wire. So the bigger the Play-Doh resistance, the more resistance. And then also we ran a wire through the Play-Doh to connect to uh, the alligator clips. Um, and the connection of the Play-Doh to the wire changed how much resistance there actually was. So then there's also bad connection of the alligator clips, which could lead to some error. A malfunctioning multimeter, our first multimeter, was broken and did not work. And then also we were told that the fan sent a current backwards, which could be seen by the fluctuating values of current and voltage over time as the fan continued to run. And then also battery degradation as batteries are used, the amount of voltage in them is going to change. And that's all. Thank you.